Welcome back to Cloud Computing and Big Data, our Lecture 3, Apache Spark for Cloud Applications, the second part of it. And the first part was really thinking about what we had in Lecture 2, so building on the idea of really machine learning fundamentals, linear learning models, so linear in the weights, and essentially having then something where we gradually build it up, the idea of using this kind of very simple models, with machine learning. Logistic regression was one of the very simple models, building on the linear learning models and using the logistic function, to determine which class it is. So binary classification problems. So blended with the idea of machine learning, of course, we want to motivate why we want to do cloud computing. And I think essentially in part 1, we explored this a little bit by using the Copernicus Marine Data Repository with some of our application use cases that we have really in research, which is the SME Greenfish, which some of you also use in your industry project. So this is really interesting because you have seen quickly by accumulating some of these data sets which are relevant, like sea surface temperature, or maybe for some advanced studies, which we use maybe in high performance computing, you want to have the ocean waves, right, data. So then you quickly come from, a couple of gigabytes to the hundreds of gigabytes and to terabytes. And that is usually something where Google Colab is not working anymore very nicely. And also we have explored, in addition to that, the GPUs you acquire are always changing. And if you want to have really, let's say, more powerful GPUs and a more deterministic way of getting them, you really have to subscribe. So you pay already for Google Colab Pro and so on to get some more resources, but you're essentially stuck with one GPU, with one resource. And then the idea of the initial part of Lecture 3, Part 1, was really to think about scalability. So how we leave that space from Google Colab and rather use something called Microsoft Azure, a cloud computing vendor. There are many of them, and the service they offer is HD Insight. It's just one of an example. We could do several similar things in AWS and actually Google Proc services. But here we want to have some practical details shared. So hence we use the HD Insight to set up an Apache Spark cluster, quickly realizing that it's in our hands to think the scalability, right? So how many worker nodes you really need for your application domain problem. Everything else is given by Spark, the ML library, machine learning library that you need for the algorithms, the whole engine of distributing tasks across your different worker nodes, managing them with Zookeeper, managing them with head nodes. This is all given by Apache Spark. And then we also realize that depending on the scalability we need, we can scale up, scale down, shrink the cluster, expand the cluster with worker nodes. We realize that the costs are then accumulating. And this is even true if you use Jupyter or not on it. So this is an important fact, also differentiating a lot from this Google Colab, that in the background, the cluster is still running every single day, 24/7, accumulating costs, whether you use it or not. And this is something important, when you go to the production, when you want to take this knowledge you get here from the course and put it to a real company, just be careful on it. And in order to, be a little bit aware of this, there's a way of getting quotas so that you really understand, okay, now I'm increasing my quotas. I use these quotas, meaning also that more and more costs will come. We also ended off with the idea in basically the first part to have a bit more systematics of machine learning. By now, you have seen many different lectures by Andy. You have seen the Agile Project Management from Ingolver. You have seen the industry project with some data here and there available and potentially already initial idea of machine learning algorithms. But where does it fit all together, right? So where are all these mathematical building blocks that we now abstractly put here on slides? That is something what also will be the goal of the second part here in Lecture 3, to advance from this. If you remember, or if you have seen the first part, we essentially started just with a training set, with a data set that we have available. And now we would put around this all other elements that we need, like machine learning models, machine learning algorithms. They always go a little bit together. Then, of course, we will have hypotheses. So, different ways of modeling, and we maybe put one hypothesis out of many to be the final model. So lots of these elements which are relevant for us, also blending in it, essentially, of course, what you do in scalable cloud computing. Hence, we talk about pipelines and so on, connecting more to our application domain, example that we had from the food inspection. So let's go with the second part. Basically, starting now with the Spark session. If you remember, we have created the subscription. We have basically also, created the Spark cluster. It's now running. And then you press on Jupyter, and then you want to start, having your PySpark session created on this cluster and connecting it. And here, if you do this in step 1, you see we import here different parts of the Spark distribution of the Apache Spark, basically tool. The open source tool is a machine learning library. We import their pipelines and a classifier for logistic regression. This is all what you know. A little bit new would be perhaps the hashing and the tokenizer we will talk about, because we have some text data and we want to have a, let's say, dense representation of the text. So we'll do there a bit what we would call feature engineering. And then from SQL, we have some data sets we want to work on. So hence there's several different functions we want to work. So when you start this and execute it in your Jupyter notebook in this HD Insight, and as I said, you will also do this practically as one of your assignment, then you basically suddenly see also difference very quickly to, Google Colab, for instance. You see here yarn application ID, meaning that your application is now connected to the scheduler, right, that I was mentioning, or the cluster manager, yarn, right, that you have here. That is now managing all your different worker nodes. And if you remember, we had said we had 3 worker nodes. So they are accumulating bravely costs, as we discussed. They're running there. And then we want to do something with it. And, this is now something where this is starting the Spark application. And the key thing out of this would be that Spark is just available now, in your session. What you can then nicely use, for instance, here with Python in the Jupyter Notebook environment. Again, I mean, there is now a lot of elements where, we can, build on what we know from Google Colab. So you operate essentially the kind of idea of this, like you had in Google Colab. The same idea was using Python. But in the back, you will operate on, this cluster element. And sometimes you would have, also opportunities to use the Hadoop distributed file system in production. That is something what we leave out here a little bit, because this will be coming later when we talk about MapReduce and Hadoop. So in the moment, we focus a little bit much more on the execution of machine learning using this worker nodes and so on. So also, if you remember, the application data set would be now something you want to analyze. Remember the CRISP DM process with the application. We have already a business understanding, which is the first phase. Now what we have to do is to load the data set, to check the application data set, and then also determine a little bit, what could be training examples and what could be test examples, right? We have in machine learning always this kind of element. We have training and test sets. If you go to more advanced machine learning courses, you would also set aside some validation test if you can, right? If you have lots of data available. For the sake of this course, we don't go in too many details, but this is really important for machine learning experts to realize it's not just training and test sets. So there are 2 files available from our application perspective, and these are available in the sample files here. So we use a food inspection data one, which is a comma separated file, and we parse this here with a small helper function that you have here using the string IO and so on. So it's not rocket science really, but you have to execute it in order to have this food inspections. And this is really just the training set we will now work on. There's another data set available that we, so to speak, throw in the corner that we don't want to know about. Just at the end, when we have built the model, we want to evaluate if our model is very good. Then we take back the test set and so on. So we ignore the test set part of the training examples in the beginning, to really learn from data from the training set. And this has many different reasons. Basically, we have to really keep these separate in order to make a honest prediction what we can do with our model with unseen data, right? If you would use the whole training examples, your modeling and your training has seen all the examples, then there's nothing to test with for unseen data. And you remember what we said in the beginning of the course, machine learning is not explaining the existing data, it's rather creating a model from the parts of the existing data really to get unseen data right. That's a very important difference. So here we could use a Spark context, SC, that we have now available, the Spark session connecting to it, which in our case here is actually connecting us with this HDI samples in a Windows Azure storage blob. That is, a kind of other service that is available that we come later also in the course when we talk about more services. And in a similar fashion, you would do it in Amazon, where you have essentially the S3 interface. We will also talk about and having similar aspects really done. You would, go back to your CRISP DM model. You would think about, okay, now I need to have a data understanding. So what data is there? So usually would, take maybe an inspection. You would print it out to understand it. You will not learn all the inspections by heart, and you should not, because a human also is learning from data in a way. So the idea is to really don't contaminate this data as it, but get a structured feeling about the data. So what attributes are there? What are generally the people talking about? You see here walls, ceiling, attached equipment, good repair, surfaces clean, dustless cleaning. There are lots of elements inside that gets you a little bit now an understanding, but you should also do in your assignment on that. And to basically, understand what data you basically work with. And when you now take the inspections that we just loaded and take one here, you see also then suddenly the job will be executed on a cluster, of course, right? Also a different story than you had before when you could use Google Colab. So here you see Spark has 6 executors, 15 cores running, one job is running to really take these inspections and print it out. So hence you see the more you do really and execute some really, more or less computing task, even if it's very simple with take one, the cluster is active, right? And basically executes, even if it's just a printout here. So from that, we also understand really the data set better, right? In the sake of time, I go not through everything here. It's also part of your assignment to understand this. But there are a couple of fields which are very valuable to us in addition to the idea and the name. There's, of course, results and violations, because this gives us also some indicator where probably the food inspection will go wrong, right? If you have violations, obviously this has some role to play in our final classification of saying, yes, food inspection was working, food inspection was failing. And we have a little bit here, attempt tables count the results. So when we look at this, we want to see here a little bit of class distribution. That's why we do this, right? For some of you, it's also important in the industry project to consider this, where we want to understand here, so how much actually we have around in the idea of, the number of classes. And interesting for us is also, what we would understand in a way, if you have a binary classification problem, we need a fail and a pass class, right? And if you look on the data sets now, ID, name, results, what are the violations, dishwashing, facilities, whatever, too dirty, whatever. So this is now a better data understanding. So we're quite deep nowadays here in this, but we also have to start thinking a bit about data preparation here. If you want to have a binary classification problem, so food inspection fails or passes, what data is available there? And is it really true that we have these two data classes, right? Hence, this is another part now where we have to do the data preparatory step, already thinking more about the modeling. So we connect in a way also these three and think about, okay, what would be now a solution tool we can use, a hypothesis set, in order to model this, right? And you do binary classification in many ways. You can use support vector machines with 2 classes. You can use neural networks with 2 classes. In our case, we use a logistic regression model, and all of these are different hypotheses that you can use, right? And the weights, let's say here in the neural networks or in the logistic regression, all the different numbers, values of the weights will be also different hypotheses. Hence, there are a lot of hypotheses in our hypothesis set that we can pick. We as a human pick already the logistic regression, but this is still a very high level pick because the correct W's all mean H1, H2, H3, etc. So first have the model, and then within the model, the different W's will also be different hypothesis set. However, what we want to achieve is from all of this learning, which is basically more or less an infinite M different hypotheses, we want to pick one that is, we say G that reasonably approximate F, which was, you remember our unknown target function that we will never learn, but at least approximates this function relatively well. So this would be next mathematical building block to think about, that you have a huge level degree of freedom to pick support vector machines, logistic regression, artificial neural networks. And within this, you would have artificial neural networks, lots of layers, support vectors of some kind. There are lots of ways how you can influence the hypothesis, essentially, and how it's trained. And then even every trained version of it would be another hypothesis. Hence, we come quickly to this M, more or less infinite ones. But we will find some solutions where we can get them to one that we can pick, which is then G. So let's put that in our practical machine learning overview, right? So this is something what we have definitively from our skill set as machine learner. What is the side of ideas, formulas, if you want, where we start from. So support vector machines, artificial neural networks, transformer models, all of these different models, they live in this space, and we have to pick one, G, out of this, that hopefully approximates F well to get the data right. Obviously, here's something missing, which is a learning, right? And we will come to that. But this is the next basically ingredients that you have seen now that also is relevant a little bit for your data preparation again, because you have to model the data according to what basically the model can really take as an input. Let's have that as an example now. So we said we have a binary classification problem. We said we want to use logistic regression for it. So it's a two-class problem. We can use a logistic function. And then we now look at the data set and the data samples a bit more careful by using, different, data frame outputs here to see the distinctness. So what is with the results? With the results is a label, right, which we expected to be pass and fail. But if we look on the data, it suddenly gives us 5 classes: fail, business not located, pass but with conditions, out of business already, pass, etc. So 5 classes will not work with our classifying problem. Hence, in the CRISP-DM, there's now a mismatch of saying we have a good data understanding, but the model we're going to want to use and the data preparation I have to do for it, it doesn't match with the idea. Hence, we have to do data preparation now to actually get these classes right, to have a concrete pass or fail. I'm not interested in, say, pass with conditions and this kind of idea, even if the data says it. Hence, what we can do here is then, of course, get a better understanding of the class distribution. You would do this in a practical application problem to really understand, is this significant? So are really so many out of business? Are so many, just passing it with conditions? And I think here the pie chart in a way gives you a very good indicator that essentially these, let's say, classes are anyway a little bit underrepresented, right, in the overall picture. Many of them pass, many of them fail. But these 3, let's say, specific classes we are not at all so interested about. And in one respect, we can even say that the pass with conditions, right, which is quite here, could be even modeled with pass because it passed in the end. So once you do this, and I think I'm not explaining this a lot, but you see that Spark is always using this execution distributed with different tasks. And essentially, once you do the practicals, you get a better feeling for it. Get your understanding of this remote execution and scalability, because now if you would have, let's say, terabytes of data to get these results would fill the cluster quite some time, right? So the duration would be perhaps not 6 seconds for one. So it would be maybe an hour or 2 to go through terabytes of data to find out, are there different results than, just pass and fail, because essentially we command here to go through the all, data sets. And there are different tricks, lazy loading, some of you know from the industry project and so on, etc., pandas tricks to get this data frame right, especially if you don't have, let's say, just a couple of megabytes like in this application problem, but if you quickly go to gigabytes and so on. But long story short, 5 classes will not work. We have to think about that, how many are there really, giving the pie chart, and we see that out of business, past this conditions maybe still a little bit significant, but business not located are just 6. So this is almost negligible in our problem. So we can do some data preparation now to join these classes and basically drop some if you want. So basically you see that here the label for results that we are doing here in the code from PySpark is essentially now collecting some of the data. Where it says fail, it will be 0, and where it's passed with conditions or pass, we give 1, and all the others are -1. So hence this what I thought taught to you, the, let's say, less significant ones. And then you just basically drop the others, select those results which are above 0. In other words, we don't care about the -1 types like the business not located and so on. With this, I create basically what you see here, the binary classification problem again, by modeling this a little bit for mathematical convenience here, 0 and 1, right, as different labels, fail and pass. And I merge with the pass with conditions because I think usually the restaurant owners will probably also do anything to stay in business to pass. So this is a typical data preparation step. So that was an example of class imbalance, where you would say some of these classes are not important for us. You would sample them out. You would, prepare the data set again in the CRISP-DM idea to do the modeling step. So once done this, it's good to have the understanding now that, we have really, of course, removed some samples, which is always handled to be careful in machine learning because it could be, something which is of value. But we did visualization, we did the data analysis and learned that actually just 6 out of business cannot make a big picture nor a big problem. And by having now something what we have in the data, then we have this pass and fail, the 0 and 1. We need now a binary classifier. So hence we come in this step 5 now after all this data, analysis and visualization process now to the idea of picking one of the hypotheses, right? And this is modeled in red in a sense because every time we change the W, we have another hypothesis. Right, so we said before the logistic regression is actually still, relatively simple. It's a simple linear learning model, which we put now with this, idea through this logistic function. And, then you have some couple of parameters that you can use, and it's nicely already provided to you in the Apache Spark implementation. So hence the whole algorithm, the model as well, as optimizers is something what we have already available. So we just pick the logistic regression now and say that is an overall hypothesis set, understanding that within this, when W changes, I have lots of these logistic regression outputs, right? So hence we have to find a, let's say, learning algorithm that gets the W's right in order to determine what is now the final model. To put that more in a production way of thinking in cloud computing, we also add something what we now say is something very useful if you want to put that in a deployment in step 6, right, in the CRISP, in the last one, where you really want to do it and execute it on a daily fashion. So you don't want to play around again and again with the Python script, massaging the data again, inspecting the data again. So here you have a certain pipeline which is relevant for the training and for the testing process, right? For training and testing, we will start with the training process that you have here on the upper part and then come back later to the testing. But this is something what you want to systematically create with your Python, script so that it can be executed maybe always on a daily basis with new unseen data. But the idea how you transform the data, right? For instance, from the raw text of the violations, we go with a tokenizer to words. We have this a little bit here in the hashing tokenizer idea in the Python code here on the top. And this is also executed on the cluster, but you see a kind of nice visual representation how it works. You create a so-called feature vector out of this. So to understand, clean, 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 this might be very good, but also dirty, dirty, dirty can mean for the feature vectors and the words you actually get out of the text quite bad. So hence this feature vector will influence, a lot. And because we, for mathematical convenience, don't want to really work with the words, and this dirty and clean and so on, we have this hashing function we put over it, making, let's say, a more mathematically convenient idea how to work with this, let's say, feature vector. And then the whole process starts when you put it into a logistic regression model, right? This is just the model, which is a linear learning model, we have said, and then putting it into a logistic function. But we need also something to learn, right? So for each of these different machine learning models, so the blue one here, we would have usually something red, which is then the algorithm, which in our case is then also the logistic regression idea of doing, let's say, iteratively optimization. And this is something we had the last time already, basically taking derivatives here, and which is known, at gradient descent, more, let's say, faster version is stochastic gradient descent. Then new optimizers like Adam, which takes some momentum and so on, where you go downhill, the errors will face. So this is also something where we cannot spend very much time on it, because machine learning courses firstly should do a hell lot of this, and optimization is also in other courses. But this is something we can take out of the box, is also available already in the Apache Spark distribution, and we can just simply reuse it. What's missing there is, of course, the error function. Hence, when we want to learn, it's a very important measurement for us, right? So we start with the training examples. Okay, yes, thank you very much, we know. Then we said we pick the optimizer, which could be SGD, let's say, as an example for doing what we see here, always taking, for all of the different values, then the derivative, and then updating essentially the weights always with, a certain times of learning rate and the factor, how much you want to learn from the, going down the error slope. But what's missing there is, of course, then the error function, right, that we want to achieve on it. So here is a logistic loss function that is typically used like this, and evaluated also on the Y, on the label, that basically gives us then an expression of saying how wrong are we. And this is a sort of thing that you also have to pick, and it needs to fit a little bit to your application domain problem, right? But so hence the machine learning inherently here is nothing else an optimization problem of, basically getting less loss, or basically getting less error. And instead of the perceptual learning algorithm, if you remember, add, subtract a vector, add a vector, subtract a vector, which was, let's say, a little bit simplistic, and as I told you, also just works actually if the data is linearly separable. We want to have here some way of really having a more professional approach, which is then this optimization, which is a little bit mathematically more elaborate, and of course taking derivative. This evaluation is then also where the computational footprint is increasing. Hence, if you now have lots of data sets, in the gigabyte regime, this is something which you also have learned, I guess, more or less in the lectures from Andy. This is an increasing factor, right? So you have learned the artificial neural network, back propagation of error, going through the different layers. And there you do also taking derivatives and, update the weight vectors. It's the same process. Here we stay very simple in the logistic regression, but for Andy's backpropagation of error through a let's say, layered neural network, this could mean a lot of computing already. And this is something which we will later on connect also to the GPUs again. That's why in machine learning, it is nicely computed on GPUs and so on. So now we have picked a lot, we have worked a lot, and we have seen that Spark gives us lots of tools. So this tokenizer to create this interesting, nice pipeline where we use logistic regression with. So you see the pipeline comes all together. The first getting from the words to this idea of a hashing, function. And you put this all in this pipeline that we now can execute in with pipeline fit on the labeled data that we created before, basically getting the data together with fail and pass with conditions. So hence, these violations are now really a condensed feature. And what we steer here a little bit is the iterations of the logistic regression. So how often I go through it, and regularization parameters, so it's basically the margin of error and so on you allow to know, not learn by heart. Regularization and validation are also topics that need to be taught by a machine learning course, much more longer than I can do here. But let's say the professional people always more or less use regularization and validation. So it's a very important topic, and you see we even use it here. And it has something to do with data not overfitting. So in a way, you can say regularization and validation combat essentially overfitting of data. So to not report something which is really not really learned. But again, the machine learning courses need to go there if you're interested in this much more deeper, really to the bottom of this. For us, it's important now to say in Apache Spark, we have this nice pipeline, and now actually you see that here the Spark is very busy executing, 13 jobs completed, because there's now, of course, much more things to do. Hence, the jobs are much more, and there are many different tasks executing. Again, I think when you use it in a practical way, you will see and get the heck of it. Now we can also model this a little bit more explicitly in our practical overview. So we have an hypothesis set where we said, okay, logistic regression model, perfect. And we have this learning algorithm, which was this optimizers to the logistic learning model. We had this in our linear example before, right? There was a perceptron learning model that we had as hypothesis. And then we picked the perceptron learning algorithm, this adding, subtracting a vector. This is an example. Now we have logistic regression, and we add the logistic loss function that will be still missing a little bit, an error value that will come next. But we already know that we can use optimization with logistic regression here in order to be our solution tools to get from the training examples to one hypothesis set if we optimize well at the end and pick the one that is trained after 10 iterations to be ideally the one that approximates F, the original target function, very well. And with this, the data and unseen data. So let's put that in our practical overview. The hypothesis set here, the learning algorithm, that also something we have to, of course, pick. But in addition, and this is important for you, the process now getting from this learning algorithm to the final hypothesis can be computational intensive, right? While the training examples put demands in cloud computing for storage, the learning algorithm, right? So what you have seen maybe also with Andy, vision transformers, autoencoders, attention mechanisms. These are all computation intensive by orders of magnitudes where you need a hell lot of GPUs to get going. For logistic regression, our course assignment, that's relatively easy. Still, you see already an intensified more use of computing power. However, we're not done yet. One of the things I left a little bit out here in this was the error measure, right? Which was a logistic loss we have to have in order to optimize, because we want to have less, basically error. Hence, in this iteration of this 10, we always will evaluate against this error function, which, is also nicely given by the Apache runtime and should fit a little bit to the model you use, which in our case was very clear. We use a logistic, ideal logistic function with a linear learning model. But we could have picked support vector machines, for instance, and then you would have the quadratic optimization, right? A different way to do optimization with high-level feature spaces. So it really is something which you have to pick depending on this. And you will also carefully notice that usually Apache Spark will have not a parallel support vector machine. We do this in HPC and have one available, PSVM, which is then parallel. So basically support vector machines are not really available in Apache Spark, but logistic regression is, and trees, random forests are, and many others as well. So this is all important. Hence, we have to add this to our way of how we see the practical machine learning problem, because the error measure might be also very application specific. You want to have maybe some error measure that says, when you break into some huge house, then the error might be, which is very sensitive, much more tuned to the break-in of data analysis, in all your historical break-ins, because this is something you really want to avoid. Or let's say in healthcare, right? One error in having a patient analysis wrong might be a life. So this error measure is a bit flexible. And again, machine learning courses should talk much more about it. But this gives you a relatively good picture where all the different parts are. Adding also the probability distribution that, in a sense, what I'm showing you here is the so-called PAAS learning, probabilistic, approximately correct learning, assuming that the training samples we have that was given by this unknown target function comes out of the same probability distribution on X. So hence, when you do Netflix movies, don't necessarily do them with some other streaming provider and analyze this, because there's a different probability distribution. Other people may be looking this, and so on and so on. However, these are the constants in learning given to us, and we have to work with this, and this makes it working. All right, so just to understand also that the target distribution is never correct, from Netflix as well, some people, or, you can even be the same person, so the same ex-in, same person, same movie, saying the movie is fantastic, and you look at the same way maybe after 2 years, and you don't like the movie. It's still the same ex, the same person, the same movie, doesn't like the movie. So hence, this would be not a function anymore. Hence, you put the probabilistic assumption plus noise around it to be, let's say, safe with practical data, right? At the end, we want to, analyze then what we have done. So in this regard, we come to the next step, which we now pull in our, back of the class in the corner somewhere, this rusty test set we didn't use. So we have trained the data with logistic regression, with the stochastic gradient descent. We have a good model now, we think, with a fit, right? That was one of the Python elements on it, and out of it comes a model. Now we have to learn basically if that's really true and evaluate. Hence, we look at the test set. Now, the test set is something here, what you see again, is another data set, food inspections 2. But of course, it's inherently the same way structured, right? Hence, if you inspect it, if you look at it, it has the same results, fail, pass, etc. Probability vector that we create now, basically here, gives us then the opportunity to understand a little bit, again, what was essentially the label, right? So what is a prediction, pass or fail? So this is something where we now take a complete different set of unseen data, but of course it should be structured the same way. And as we said, with a probability distribution, it should be not now maybe, food inspections of New York, because we have the data from Chicago. However, chances are that this might be still related. In our pipeline analogy, we now want to see if we cannot use essentially then this pipeline again, right? So do this kind of idea with the whole process going through the data again by using then this text file that we have before, fitting it with new data and using the transform function. So this gives us then the opportunity to essentially use then this kind of pipeline we have created again. But the difference now is, of course, we have the model available, right? We trained that already. Hence, here we reuse the model in Python, transform, of course, in the test data frame we have used here, and essentially then have the prediction that is getting out with new unseen data, which is our test set, and can now evaluate and work with it. And that's in a way how the machine learning works, right? And basically in the background, you will see now many jobs, when you execute this also with your assignment and so on, that will now get for the statistics and for the evaluation some, true positives, false positives, and so on. This is one of the metrics that you can look at if your modeling is correct, but there are lots of model evaluations. Hence, this crisp DM step, if you want, is very rich. You can have lots of different evaluations depending on the application domain problem, F1 score, etc., etc. Also, this is, of course, something what a machine learning course can teach you much better, and also is going into it. We take a very simple one called the confusion matrix here with true positives, false negatives, false positives, true negatives. You see that here. if your classifier prediction is actually from the labeled data correct or not, or if it's basically correct, but in our prediction, unfortunately, wrongly classified. Hence, you would have interesting like the true positive, which should be like this, and the true negative, which is, of course, then true, so really good learned. But unfortunately, we will find out there are also false negatives and false positives. Then you can put that into a sort of ratio, right? So how much are really, basically done here. And this is something also you should explore a little bit in your assignments. So I will be a bit quicker here. And again, as I said, this is something where you could have different evaluators. But you have seen that everything is basically done in the cloud remotely, that we used Apache Spark quite conveniently, right? So the machine learning algorithm was already there. We don't have to implement it. The loss is already there, the loss function definition. We had the optimizers, SGD and others already available in Apache Spark. And all of that is now independent in a way from the size of the data. This was very simple data sets, but Apache Spark can do much more. And I think this video shows you a little bit what more you can do essentially when you go to the production field. And you will also learn more and more that Apache Spark is used quite broadly. Here's an example from Databricks in practical applications on a daily basis for very different data analysis, right? You see here some examples, and the video will show you also in detail. So we leave here today also to have to understand, better virtualization, multi-tenant clusters, cloud computing topics we will actually explore in lecture 4 that we will have on Thursday. So talk to you then.